In this video, we will talk about a harder definition of the derivative example. So in this example, let c of x be equal to x cubed minus 4x be the cost in dollars of selling x items. I want to find c prime of x using the definition of the derivative in part A with the limit as x approaches a. Okay, so we've seen two forms for the definition of the derivative, and one of them involves the limit as x approaches a. So let's remind ourselves what that was. So the derivative of our function at a is equal to the limit as x approaches a of c of x minus c of a over x minus a. All right, so that's our definition of the derivative. And now let's begin to evaluate this. So we have the limit as x approaches a. C of x is our function, so that's x cubed minus 4x. So that's the c of x, and then I have to do minus c of a. So let's make sure I put a parenthesis so I don't forget to distribute the negative. So c of a means plug the a in where the x is into the function. So that gives us a cubed minus 4a, and then all over the x minus a on the denominator. So putting that parentheses there is super important. If I forget that parentheses, I'm probably going to forget that I need to distribute the negative. Alrighty, so simplifying this, let's go ahead and distribute that negative. We get the limit as x approaches a, x cubed minus 4x minus a cubed plus 4a all over x minus a. Okay, so this looks a little bit challenging to simplify, but what I'm going to do is focus on the numerator. And notice that the numerator has 4 terms. And a common strategy that we can use to factor things with 4 terms is to try factoring by grouping. So we're going to try to group this. All right, so when we group something, we have to first decide which way we're going to group it. So are we going to group the first 2 terms together and the last 2 terms together? Or are we going to do like the first term with the last term and the middle 2 terms together? Or we could even do things like put 3 of them together and then leave one of them by itself. So we have to decide what grouping we are going to choose. So let's just say I choose to group the first 2 terms together and the last 2 terms together. That's often like our first attempt. So there's one important warning that I want to give about factoring by grouping, which is don't put parentheses around the groups. Since if we do that, we'd have x cubed minus 4x parentheses and then times negative cubed plus 4a. And when we put the parentheses there, that means something different. That means we're multiplying the first 2 terms with the last 2 terms. But that's not what's going on in our expression. They're not being multiplied. So I want to avoid putting parentheses around the groups because that changes the meaning. This means something different. Something different. And let's go ahead and put a bubble around this. All right, so let's try this grouping. So what can I factor out of my first group? Well, I see an x is common, and then I'm left with x squared minus 4. Out of my second group, I could factor out an a or maybe a negative a. So I'm not totally sure. Maybe I'll just factor out a negative a. And if I do that, I get a squared minus 4 left over. And the next thing I have to ask myself now is, when I look at this first group, so here's my first group, and I look at that second group, do they have any terms in common? So for example, if I look at this first term, this x, is there an x as one of the factors in a times a squared minus 4? So the answer to that is no, there's no x. And I also see x squared minus 4 here, which I could factor as x plus 2, x minus 2. But neither of those is a factor of this second term. So there are no common terms here. So there are no common terms. And all that means is this is the wrong grouping. Okay, so we're sad about that. We tried this. Our first attempt didn't work. But that's okay. That's okay, and that's common in math problems in general. Sometimes the first thing that we try won't work, and then we just have to try something different. So in this case, our first grouping didn't work. Let's try another. Okay, so we won't give up. We're going to try another grouping. All right, so now let's do attempt 2. So at this point, I want you to pause the video and see if you can identify what a better grouping would be. So pause it for about 2 minutes to think about this. 4, 3, 2, 1, pause the video. Pause it for 2 minutes and try to identify that better grouping. So while you're doing that, I'm just going to copy down. Actually, no, I won't copy anything down. I'm going to let you think about it. All right, so hopefully you've done that. Hopefully you've paused the video to try this for about 2 minutes. That likely wouldn't have been enough time to finish the problem, but I mostly wanted you to focus on how you would begin, how you'd identify that correct grouping. So it turns out the grouping that's going to work is if we put the x cubed and the a cubed terms together, so the x cubed minus the a cubed, and then the non-cubed terms together, minus 4x plus 4a. Because the cubes factor, this is a difference of cubes, which we've seen before, maybe several lecture videos ago when we were reviewing our algebra. But difference of cubes, that's something that we've seen before. So how did that factor? So that was x minus a times x squared plus, xa. Ooh, sorry, my screen just got shifted over there. Plus, so that's a squared, and then xa plus a squared. And then from the minus 4x and the plus 4a, I could either factor out a 4. If I factored out positive 4, I'd be left with negative x plus a. Or, and if I look at that, I notice that my first group and my second group don't quite have something in common. But one of the factors is off by a negative sign. The x minus a and the negative x plus a, they're off by a negative sign. So I actually could have fixed that by factoring out not positive 4, but negative 4. And some of you might have noticed that, which is awesome. But okay, even if I didn't notice that right away, that's okay. Quick fix. So factoring out the negative 4, I'm left with x and then minus a. And now I see a common term. I see a common term. In the first group here it is x minus a, and the second group there is also an x minus a. And when there's a common term, we get to factor that thing out. So factor out that x minus a. And that'll leave us with the x squared plus xa plus a squared from the first group left over, and then minus the 4 from the next group left over. And now we've successfully factored this by grouping. So let's put this back in our limit. So we wanted to do this limit, and now we know how to factor the numerator by grouping. So here's the numerator once it's factored. Okay, and as we've seen before in these difference quotient expressions, now that we're applying them to this limit definition of the derivative, typically something on the bottom and on the top is supposed to cancel at the end of this. And now I see that this x minus a has been factored out. That cancels with x minus a on the bottom. After they cancel, we are good to plug in. Now, the problem that was there before when we tried to plug in a, that made the denominator 0, that's gone. So plugging in a for the x, we get a squared plus a times a plus a squared minus 4, which is 3a squared minus 4. And that is our derivative. But remember that originally in the problem, the variable was x. So we should now rewrite this in terms of the original variable. Because what this tells us is the derivative of our function at a is 3a squared minus 4. That's what this tells us. But let's just rewrite this in terms of x. Because that was our original variable, we'll get c prime of x equals 3x squared minus 4. All right. So in this video, I want to show you what this would look like if we had used the other definition of the derivative instead. So we can compare and understand what are the differences between the two methods. So now let's evaluate this using the limit as h approaches 0 definition. Okay, so if we use that definition of the derivative, whoops, that's not how we spell it, definition of the derivative, we get c prime of x equals the limit as h approaches 0 of c of x plus h minus c of x all over h. That was our definition. All right, so now let's start to evaluate. We have the limit as h approaches 0. C of x plus h means take that x plus h and plug it into the function for the x. So anywhere there's an x, we're going to plug in x plus h. That gives us x plus h cubed minus 4 times x plus h. Okay, so this whole thing here, that is c of x plus h. And then we have to subtract c of x. So let me zoom out a little bit to give myself more room. C of x, well, we know what c of x is. So I'm deliberately going to make an error. And let's see if you can spot my error. So minus c of x. So minus x cubed minus 4x. So pause the video for 30 seconds and see if you can spot the error I just made. 4, 3, 2, 1, pause the video. Pause the video for 30 seconds and see if you can identify my error. So hopefully you did that. Hopefully you've paused the video for about 30 seconds. The error is I forgot when I subtracted c of x that I'm subtracting this whole thing, the x cubed minus the 4x, so I need to put a parentheses around it. If I don't, I'm going to forget to distribute the negative to both of the terms. All right, so now I have that in there. So this, the x cubed minus 4x, that was the c of x we were subtracting. Okay, all over h. All right, so now we need to evaluate this. We have the limit as h approaches 0. So, I see the negative sign. I'm probably going to have to distribute that. Probably going to distribute the negative 4. And then I have this x plus h cubed. Well, how do I work out x plus h cubed? That means x plus h times x plus h times x plus h. And if we do some algebra, if we FOIL out two of these terms first, and then multiply it by the last x plus h. So I'm skipping that step. But if we did that, it turns out we get x cubed plus 3x squared h plus 3xh squared plus h cubed. So I'd encourage you to actually multiply this out on your own and verify that for yourself. But after two steps basically of multiplication, we get that. All right, so using this, the x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. Then if I distribute the negative 4, we get negative 4x minus 4h. If I distribute the next negative, now we get minus x cubed plus 4x. And then all over this h in the denominator. Okay, so now we get some cancellation. X cubed with the negative x cubed, and the negative 4x with a positive 4x. So we have the limit as h approaches 0. Every term that's left in the numerator now has an h in it. So we can factor out an h. And that leaves us with 3x squared plus 3x plus h squared and minus 4. All over that h in the denominator. But now, again, this term on the denominator, now we are able to cancel it in the numerator. And that's typically going to be basically our second to last step in these definition of the derivative problems, canceling out that thing in the bottom. Okay, so now we've canceled that out. Now let's try plugging in 0 for the h. So we get 3x squared plus 3x plus 0 squared. Oh, whoops, I think I made an error actually. Hold on. Yeah, this shouldn't have just been a 3x. So that was, let me point this out. That was coming from the 3x h squared. And when I factored out an h, I should have had 3xh. Okay, that's good. That's good we caught that. All right, so this should have been 3xh. Okay. But I'm plugging in 0 for the h, so this should have been 3x times 0. And then h squared, when I plug in 0, I get 0 squared and minus 4. So now I think that looks good. And simplifying this, we get 3x squared minus 4. And if we zoom this out, you might notice this looks like the same thing that we got above. So our derivative function, c prime of x, equals 3x squared minus 4. So now let's recap some key takeaways from these two forms of the definition of the derivative. So there are two key takeaways. When we do a limit definition of the derivative in the first way that we did in this video, when we take the limit as x approaches a, that typically involves more factoring. And in this example, we had to do it by factoring by grouping, which we won't always do because we won't always have 4 terms as we did here. But it typically will involve more factoring, but overall less terms. So if I just scoot it back to where we were, notice that in the numerator, I just had these 4 terms that I was working with. And that was less than how many we had here. After we did this mass expansion, we had way more terms in the numerator. So that's a key difference that often shows up in the two forms. And in the second form, when we did the limit as h approaches 0, we typically will have to expand more stuff, so multiply more things out, and it'll have more terms. All right, so there's one final part to this example that I want to do, which is an application question. So let's find and interpret c prime of 5. So let's remind ourselves what our derivative function was. So we got that c prime of x. Let's put this in a different color actually. We got that c prime of x equaled 3x squared minus 4. And we want to know c prime of 5. So I can figure it out by just plugging in, because I already have my derivative function. So we get 3 times 5 squared minus 4. That's going to be 3 times 25 in the front, which is 75 minus 4. And that is 71. Okay, so we found c prime of 5 at 71, but now I need to interpret this. So what does the derivative tell me? There are 2 interpretations of this. So one is the derivative tells me the instantaneous rate of change, IROC, at whatever point we're talking about, which is x equals 5. But the instantaneous rate of change is also the slope of the tangent line at x equals 5. So if we use that idea to motivate us, if I were to just draw a rough picture here, so let's just say I have my axes, and the point that I care about is when x equals 5. So wherever the point is on the graph where x equals 5, I don't even have to draw the rest of the graph, wherever that individual point is, the fact that the derivative is 71 there tells me that the tangent line at this point should have a slope of 71. So that means that my graph, whatever direction it's sort of curving in, it needs to be really steep at x equals 5. So my graph is going to be really steep here. Maybe it's curvy, but really steep. Steep enough, in fact, that the slope equals 71. Technically the slope of the tangent line. Let me just write slope for the time being though. So the slope equals 71. So now if I were to draw a tangent line here, okay, so this pink line, that is our tangent line. So the slope of this tangent line equals 71. So our actual function, this blue graph, may be curvy. It might be curving up or curving down. But the tangent line sort of approximates how steep that function is at this point. So one of the things that this tells us, and this is the interpretation, is if we use that tangent line as a guide, when we increase the number of items sold from 5, which is where our point is, to 6. So when we increase it by 1, that's like where, so let's say this is where 6 is. That's like saying this distance is going to be 1. So when we increase the number of items sold by 1, we estimate, because our tangent line gives us an estimate, we estimate the cost, because that was our function, it represented cost. The cost will, because my slope is positive, the cost will increase. The cost will increase by, what were the units of cost here? They were dollars. We estimate the cost will increase by $71. And that is our interpretation. And again, we're estimating the cost will increase because the slope is positive. If my derivative had been negative, that would mean my slope of the tangent line was negative. And in that case, we would have estimated that the cost would have decreased. Okay, so our derivative here has units. So what are the units of this slope? So the units of this slope are dollars on top, because that's the change in the cost function, and over the units of x on the bottom, which are item. So dollars per item, those are the units of our cost function. Sorry, not the cost function. Dollars per item, they're the units of the derivative of the cost function. So in terms of our goals for this section, we have now talked about how to define a derivative of a function in 2 ways, using the limit as h goes to 0 and using the limit as x approaches a. In the next video, we will do a limit example that is secretly a definition of the derivative in disguise and talk about how do we recognize what function it is describing and what the point is that we're taking the derivative at.